Good morning and welcome to chapter 6. All right, this will be the first of 3 videos on chapter 6, which is entitled Z-scores and the normal curve. So before we actually start talking about what a Z-score is, let's go back for just a moment, back into your memories, and talk a little bit about a standard deviation. Remember that a normally distributed data set has essentially 3 standard deviations worth of information to the right of the mean, in other words, above the mean, and 3 standard deviations below the mean. And so if you look at the normal curve and you divide it into 6 segments, each one representing 1 standard deviation, you fit 99.9 something or other of the data into that curve. Now, what a z-score is a number that is a standard deviation above or below the mean. So the goals here in this particular chapter is to determine what a z-score is and what it tells you about a raw score's relative standing. In other words, how many standard deviations above or below the mean that score actually is. It also another goal is to determine how the standard normal curve is used with z-scores to determine relative frequency, simple frequency, and percentile. Okay. And then finally, at least on this list, the characteristics of the sampling distribution of means and what the standard error of the mean is. Okay. So again, essentially, a z-score is going to be a number between -3 and +3. All right. A -1 z-score means that the raw score is exactly 1 standard deviation below the mean. All right. And then our last goal here is how to compute z-scores for sample means and how it's used to determine their relative frequency. Okay, so there'll be some calculations toward the end of this chapter. Now, back to what we were saying before. If a raw score is 2 standard deviations above the mean, then its z-score will be +2. Okay. If it's 1 standard deviation below the mean, then its z-score will be -1. Okay, and so what the z-scores tell us is the relative standing of the raw score. All right, the actual score that somebody achieved on a test or a quiz or in whatever data set is being collected. All right, so keep that in mind. Now, before we get into calculations and actual determination of z-scores, let's talk about the idea of the absolute value of a number. All right, the absolute value of a number is the size of that number, regardless of its sign. In other words, it doesn't matter if it's negative or positive. All right, we're just looking at how far that number is from 0. So if you look at a number line, pretend that's a straight line, and I have 0 here, and then -1, -2, -3, -4, -5. All right, and then 1, 2, 3, 4, pretend that's a straight line, 5. Okay. The moral of the story here is that 5 and -5 are both the same distance from 0. All right. This is, I don't know, middle school math maybe. So for example, the absolute value of +2 is 2, right? Because it's 2 units away from 0. But the absolute value of -2 is also 2 because it's 2 units from 0. In other words, the distance that the score is from 0 is 2. Or if this represents -2, and if this one represents 2, then this distance is also 2. All right, and so that's what the absolute value deals with. All right, that's where we're starting with this. Now, we use the symbol plus or minus, okay, to represent the distance from 0. So for example, plus or minus 1 means either positive 1 or negative 1. All right, and so this would be minus 1. This would be plus 1. But they are both the same distance from 0. So plus or minus simply means the distance from 0, regardless of which direction you're going, left on the number line or right on the number line. Okay. So again, what exactly is a z-score and how are we going to address this? What do we need to know in order to understand what a z-score actually is? Well, it turns out that it really is fairly simple if you don't let yourself get confused by the actual numbers. Remember that a z-score is going to have a range between -3 and +3, where 0 represents the mean in the normal distribution. All right, so if you look at a normal curve and the mean is right in the middle, all right, mean, median, and mode actually are right in the middle. There will be 3 standard deviations to the left of the mean and 3 to the right of the mean. And we call the data point at 1 standard deviation above the mean +1. That's the z-score, +1. If a raw score is exactly 2 standard deviations above the mean, then its z-score will be +2. Okay, so this is a typical standard. This is a typical standard deviation represented as a normal curve. Deep breath, Dr. Rapp, deep breath. Now, I don't like this, all right? Remember, I hate breaking up the axes, but with that said, this is a normal distribution, all right? And you can see here that the average score for this class, let's say, is 60, all right? And it looks like it probably ranges from 0 to 100 in terms of the possible scores, but the mean is 60. Now, Slug did very poorly, all right? He scored a 35. I'm assuming Slug is a he, all right? Binky, which we'll call a female because I don't really know what a binky is, but besides the things that my kids used to suck on when they were really little. Binky scored a 65, so she scored 5 points better than the average student in this class did. And Biff really excelled. He knew his stuff on this particular test or quiz or whatever it was. It's attractiveness scores. So Biff is really good looking. Binky is just a little above average, and Slug is exceptionally ugly. All right, that's what these scores represent. Now, so what does this all have to do with z-scores, and how do we use a z-score to represent the raw scores of Binky, Biff, and Slug? Well, a z-score, again, is simply the distance that a raw score is from the mean when measured in standard deviations. Now, in the examples that I've been giving you, I've only talked about a z-score of -1, -2, -3, and so on. But you could have a z-score of -1.25, all right, or a z-score of +2.16, all right? And all that does is it tells you that it's 1.16 standard deviations above the mean, okay? And so essentially what that boils down to is that a z-score is just a location on the standard or the distribution on the normal curve, all right? And so is a raw score, 1 standard deviation or 1.5 standard deviations or 2.5 standard deviations above the mean or below the mean for that matter, all right? The z-score itself also communicates the raw score's distance from the mean, and that's where the plus and minus bit comes in, all right? For a score, it can be one standard deviation below the mean or one standard deviation above the mean, but both of those scores are the same distance from the mean, okay? And so the z-score will indicate not only where, how far above or below the mean is, but it'll tell you the distance from the mean along that normal curve. Okay. Now, in terms of the calculations of z-scores, all right, what you need to know here to calculate a z-score is the raw score itself, the mean of either the sample or the population, and then finally the standard deviation of that data set. So here's the formula for a z-score. All right, the formula for transforming a raw score in a sample into a z-score is z equals x minus x bar all over s sub x. Now, of course, z represents the z-score in this case. X represents the raw score. All right, so this is Binky or Biff or Slug's actual score on the attractiveness scale. X bar represents the mean of the entire data set, all right, including Binky, Biff, and Sluggo. And then finally, of course, S sub x represents the standard deviation of this particular data set. All right, so z equals x minus x bar all over S sub x. Now, if you're using an actual population, an entire population, and not just a sample of the population, then you would use the formula that's shown on this slide. The formula for transforming a raw score in a population, all right, and that's the key word here, the population, into a z-score is, and if you look at it carefully, you'll notice it's really the same formula, okay? Z equals x minus mu over, I forget what that's called. I think it's called a rho, but I'm not certain about that. It's some weird Greek letter. So in this case, x still represents the raw score on this particular subset of scores. Mu, however, represents the population mean. All right, remember that x bar is the sample mean. Mu is the mean of the entire population. And the little symbol on the bottom there in the denominator of this calculation is the standard deviation of the population, as opposed to the standard deviation of the sample that we used in the previous formula. But the formulas work the same way. It's the raw score minus the mean over the standard deviation. That's how to calculate a z-score. Now, if you want to go work your way backwards, and in other words, if you're given a z-score and you want to compute the raw score from it, you would use the formula that's shown now. And this is really just an algebraic rearrangement of the formula that you saw 2 slides ago. All right, so when a z-score in a sample and the associated standard deviation and mean are known, this information can be used to calculate the original raw score. The formula for this is x equals z times the standard deviation of the sample plus the mean of the sample. Now remember, the original formula was z equals x minus x bar all over S sub x. So if I want to rearrange this formula, the first thing I do is multiply both sides by S sub x, and that gets rid of the S sub x on the left, and you're left with just x minus x bar. Then you add x bar to both sides, and that leaves you with x, which is the formula that you see here. All right, so x equals the z-score times the standard deviation plus the mean of the sample. Finally, when you want to compute a raw score from a population data set, you would use the formula that's shown here. All right, again, same formula. When a z-score, the same formula that you saw 2 slides ago. So when a z-score in a population and the associated standard deviation and mean of the populations are known, the original raw score can be calculated using the formula x equals the z-score times the standard deviation of the population plus the mean of the population. All right. Okay. So that leaves us at the end of the first of 3 videos on Chapter 6. And I hope you learned something.